brief introduction. So basically, Dr. Yan is an assistant professor at Department of Mechanical Engineering from the US, and he has got his PhD jointly between Tsinghua University and Northwestern University. And his current research interests are advanced manufacturing, computational mechanics, and multi-scale modeling. And today, Dr. Yan is gonna present his recent work on additive manufacturing as well as the multi-scale modeling. So, Dr. Yan, if you are ready, please go ahead. Thank you.
Thanks for the invitation, and thanks for the introduction. So today I'll mainly present our work by myself and my group members. So currently there are 6 postdocs and 6 PhD students and joint PhD students in my group. Okay, so most of you should know, powered bed fusion additive manufacturing. So the basic idea is simple. So two major procedures. One is apply a powder layer, and second is selectively melt the powder. So we repeat this process layer by layer, then we can get the complex geometry, right? And so for the advantages or for the opportunities, you are very familiar with. So first is very complex geometries like cellular structures.
Sorry, Doctor Yang. Could you please share your screen because we still see your webcam, your video instead of the screen. Sorry for interrupting you.
Song, I think I can see the slides. Can you check? Can you click the Can you click the window there?
Yeah. Sorry. My fault.
This one, right?
Yeah. Sorry.
I think it's okay. I think it's okay. No worries. Yeah, go ahead. Please. Thank
Is
you.
it okay now? Okay, so
sorry. I see the screen now. Yeah, sorry. It's just my fault.
Oh, okay, got it. So the advantage, like first, complex geometry. Second is we have a lot of freedom to control the microstructures. For example, we just control the change the scan strategy. We can change the microstructure. So if we combine the first and second advantage, there will be a huge impact in the industry. For example, we want to fabricate turbo blades. We can control the grain to be columnar grain or even single crystal. So this single additive, they manufacture single crystal is, I think, is a pretty nice results actually from Professor Connor's group in Germany. And third one is we can design new materials. Like we can mix elemental powder, get a unique powder combination, and also we can change the composition layer by layer, point by point. So then we can get the functionally graded materials. So this results is actually done by my previous group in China. So they use electron beam additive manufacturing process. So in the bottom it's titanium aluminum, and then gradually they change to titanium 64. Okay, so and for the challenges from my point of view, so one is the repeatability in fabrication quality, like the surface roughness, pulse, and voice. And second is the difficulties in experimental measurement or monitoring. So because it's so rapid and the molten pool is small and the heating and cooling rate is very fast. And for common like high-speed camera or just industry camera, we cannot see what's going on in the molten pool. And we don't really get much useful information. And without this in-situ monitoring, we cannot achieve feedback control. And third is we don't have an efficient tool to explore fabrication parameters for new material. Mostly people do try and error experiments, like through a lot of combination of laser power and scan speed. Then we can get a small processing window. Right, so the underlying reason I think is there are too many influencing factors, and there are lack of understanding of the physical mechanisms, and also we need to find a smart way and rapid way to select and optimize the fabrication parameters. I think computational modeling is can be a powerful tool to address all these challenges. Okay, today I will just show a few examples, a few questions we tried or are trying to solve or to answer while multi-scale modeling. For example, what's happening outside, like the powder motion, surface roughness, and what's happening inside, like pores, voids, and grain structures, and ultimately what's the mechanical properties. So for the surface roughness, pores, and voids, we develop multi-scale modeling of the melting process. And for the powder motion, we develop a couple of powder dynamics models. And for the grain structures, we develop a couple of grain evolution models. And to predict the mechanical properties, we integrate process structure property models together, and then we can predict the mechanical properties from the input process parameters. So I will go through these 4 different types of models one by one, but maybe briefly because the time limitation. So that means I won't really show the governing equation for each model. Okay, so actually the melting process is a very complex multi-scale problem. Okay, for example, how the electron or laser hits the material. It's actually the interaction between electron or photon collision with the material atoms. This is micro scale. And for the powder scale, how the each powder particles get heated, melted, then flow. And in large scale, in a whole part, so what's the temperature field and what's the thermal stress distribution? So actually, we built all these 3 models and linked them together. So from the metal scale, micro scale to the metal scale, actually we upscale the Hissas model, and then from the metal scale to micro scale, we upscale like the a lot of information like the multiple size, properties. So for bottom-up approach, like from small scale to large scale, we can understand the mechanisms and predict the outcomes. If we face design inverse problems, we do a top-down approach. For example, if we want to fabricate a functionally graded material, we use a micro-scale model to design the compositions in each layer. And then we use a meso-scale model to select the powder and select the fabrication parameters. And we use a micro-scale model to optimize the experimental setup, like the acceleration voltage of the electron beam or the wavelength of the laser. So for the micro-scale model of electron beam, so we simulate the interaction between electrons and atoms. For example, okay, so this is a material surface. For metal alloys, there are mostly different elements, so different atoms. For example, for titanium 64, so there are titanium, aluminum, and vanadium. Okay, so there are different atoms. So we simulate millions or tens of millions of electrons impinging into the material, collide with the atoms. So we record the trajectory of each electrons and record the absorbed energy at different locations. And also we track the backscattered electrons and the energy it brings away. So that's the the energy loss. Then based on this, we can derive an equation for the Higgs model of electron beam. So there are mainly 4 items in the equation. One equation is the energy distribution in the cross-section of the electron beam. And then it's a energy distribution in the penetration direction. Okay, so these 2 terms are derived from this simulation results. And for the energy absorptivity, we derive actually calculate based on the backscattered electron and the energy it bring the backscattered electrons bring out. And this Q is a nominal or input electron beam power. So this is a physically informed Higgs model. So there's no much assumptions. The energy transfer from the electron to the material, that is a collision between electron and atoms. So they are basically governed by the equation from quantum mechanics. Okay, so for this micro scale simulation, so one group from Canada, they use a very similar model and they do experiments to calculate and to to validate the model. So they did the experiments and simulation at different incidence angle, from 0 to like 70 degree, and you can see the experiments and simulation agree pretty well. And how can we implement this Higgs model from micro scale to the powder scale? Okay, so for each individual time step in the model, so we construct this very complex powder free surface like this. And then we apply our Higgs model by dividing the electron beam into a number of sub-beams. And the sub-beam, the energy of each sub-beam is different depending on its location in the cross section. And then we find the free surface and start the penetration from the surface. And for each sub-beam, the energy absorptivity is calculated by the localized incident angle. So here the incident angle is here. So the incident angle here is maybe close to 0, and this incident angle here is larger. So different locations have different energy absorptivities because of the different incident angle. And then we apply the absorbed energy along the penetration distance. So this all come from the microscale simulation. And then we apply the recoil pressure. So what's the recoil pressure? Recoil pressure is when the power is pretty high, then the temperature could be very high and even higher than the boiling temperature of the material. So then there will be serious evaporation, and the material will try to become vapor and escape from the surface, from the material. So due to the conservation of momentum, so there will be a recoil pressure. So the recoil pressure is dependent on the material composition, on the local temperature, and also the ambient environment. So we apply the recoil pressure here. And then for each time step, we go through this procedure. So to ensure the accuracy, we make the time step size very small, 50 nanoseconds, and the mesh size is around 5 micrometer. Okay, so we have a couple of verification cases. So first case is we assume the energy distribution in the cross section of the electron beam is uniform. So it is irradiated on a spherical powder particle, and you see the middle part get melted first, and then the edges get melted later. This is because in the middle, in the center, the incident angle is 0, so the energy absorptivity is the highest. And go to the edges, the close to the edges, the energy, the incident angle becomes larger and larger. So the energy absorptivity becomes lower and lower. And also you can see the temperature in the subsurface is the highest. This is also agree with the microscale simulation. And for the recoil pressure, we applied a Gaussian distributed electron beam, and the power is pretty high. And you can see the keyhole here is formed. For laser, the heat source model is a different story because the energy of individual photon is much lower than the energy of an electron. So the photon cannot, really penetrate deeply into the material. Instead, just got reflected. So there will be multiple reflection within the keyhole or between the powder particles. So to calculate the energy absorptivity at each reflection, we use Fresnel equation. So it's essentially derived from Maxwell equations. And this equation we consider, the influence of material and the wavelengths and the polarization of the laser. So you can see here for this nickel alloy, for different wavelengths and different polarization, the reflectance will be different. And we also have a verification case here. So there's a laser coming in this direction. And so this is the first reflection point, second reflection point, third one, fourth one. And you can see the simulation result. So here, first reflection point get melted and even form a little keyhole, right? And then there you can see significant temperature rise for the second one and a very small temperature rise in the third reflection point, and in the final reflection point, you can barely see the temperature rise because, for example, in the first reflection, the energy absorptivity is 30%. So all in 70% come to the second reflection point. So 30% of the 70% get absorbed here. So lower here, even lower here. So this model show our ray tracing model for the laser can well trace the laser and also calculate the energy absorptivity. So with this model, we further investigate some phenomena observed in the experiments. For example, when we scan a single track, our expectation is we got a uniform straight track, right? But in reality, it's not like that. It's non-uniform, or even sometimes it's isolated droplets. So this is very harmful for the surface roughness and the dimensional accuracy. So we did simulation to reproduce what's going on in the experiments, and more importantly, we can review what's going on in the molten pool and how the isolated droplets are formed. And actually, the physical mechanism is mainly due to the lack of remelting in the substrate, and also the surface tension is the main driving force. So this is the case with the powder, because the random powder has some random fluctuation. So we collaborate with U.S. National Institute of Standards and Technology. So they do a few very well controlled single tracks on a bare plate. So that is so this case we call it constant speed case. So this is like they turn on the motor, like the laser scan first, and then turn on the laser power. So because then during the laser scanning, the scanning speed is constant. Another control strategy is they turn on the motor and the laser power at the same time. So there will be acceleration and deceleration stage in the beginning and the ending of the track. And third strategy to scan a track is the turn around. So in the experiments, in this they very carefully and systematically measure the multiple ways. Okay, like at different locations, the multiple ways will be different. So you can see the multiple ways is relatively higher in the beginning and the ending. And in our simulation, we use the same measurement methodology, and we can see the same trend. And also the mean value and standard deviation are quite close. It's for the width and for the head. And also you can see there's a peak and in the beginning and a valley in the end. So you can see the peak is around 10 micrometer and the valley is around minus 15 micrometer. So in our simulation, you can see the peak and the valley. The value also agree pretty well. For the powers, so actually, in real experiments, it's not just single track, it's multiple layer, multiple track. So maybe in one layer, the scan path is like this, and the second layer, in the next layer, the scan path will rotate for a certain angle. So in the simulation, we try to reproduce what's going on in the experiment. So the scan of the scan path we also incorporate. So this we already finished the first layer in this direction, and then we run the second layer, and you can this zoom in video is show where the lack of fusion voice will be formed. Like this is lack of fusion voice. This here. And also we can find the pattern of the distribution of this lack of fusion powers and voice, and they agree pretty well with the experimental pattern. And actually there are another different or more complex parts in the experiments. So this is we collaborate with US Argonne National Lab. They use the high-speed X-ray imaging to monitor the molten pool and how the pores move within the molten pool, whether escape from the molten pool or stay inside even after solidification. So we run a simulation to support their experiments, to support their explanation. And actually, more in depth is we found the keyhole depths. Actually, the keyhole depths will vary because the randomly distributed powder particles. So if the keyhole depths become shallower, and the energy absorptivity will become lower. So if the keyhole depths become deeper, then the energy absorptivity will become higher. This is because with the deeper keyhole, there will be more reflection of the laser, so there will be more energy to be absorbed. And even for the same part geometry, and we use same power but different scan speed. The keyhole depths will be different, so the energy absorptivity at different locations will be different. So you may ask, how we generate this very complex powder geometries. So we are not, building them in like SolidWorks or other CAD software one by one. So if we just fully simulate what's going on in the experiments. So two major procedures in the experiments: apply a powder layer, and then selective laser melting or electron beam melting. So we build in addition to the model of powder melting, we also have a powder dynamics or powder spreading model to simulate the powder spreading process. So we incorporate the elastic, inelastic collisions between powders and with the substrate and the powder rate, and also the frictions, gravity, van der Waals force, and the powder jet distribution is the same with the experiments. Also the layer thickness, rig shape, speed. So this model is not only to provide this geometry, and also we can also use this model. One is to provide guidance on the machinery design, how we can design a better powder spreading machine to make it the packing density better. And second is we can provide guidance on the powder size distribution selection. So we use this model to investigate the influence of powder size distribution and layer thickness. So we also did a variety of experiments, and we measured and evaluate the relative packing density in the experiments and simulation. And you can see for each of the cases, they agree pretty well. But more importantly, we can find the optimal powder size for this material, for this spreading rig speed. And we also review more in-depth underlying physics. So there are actually mainly three effects governing the powder packing. One is we call wall effect. And secondly is cohesion effect. This cohesion effect is mainly due to the van der Waals force between fine particles. So these two are relatively easy to understand. The third one is pretty interesting. So because generally people think bimodal powder particles, like small particles and large particles mixed together, we can make the powder bed to be more densely packed. But in our simulation we found, and also experiment we found, there is a percolation effect. That means the small particles will percolate between the large particles. So the final relative packing density for this bimodal powder particles is not higher than individual powder particles. Mono-sized powder particles. But of course, there are a few other cases. So we just invest this case. So it's not so good. And in addition to this, we can revisit here. So you can see in this simulation, all the powders don't move during the melting process. So this is relatively true in the electron beam additive manufacturing because they are preheating and sintering. But for electron beam, it's not the case. And we can see this is a high-speed camera imaging of the. You can see the powder flying. So this is very nice video is done by Dr. Wentao, I think from UK. So to investigate, actually we call this powder spattering and denudation. So to investigate this issue, so we develop a multi-phase flow. So in addition to simulate the powder motion, we also incorporate the ambient gas and also the vapor flow and their interaction with the powder particles. So this is a simulation result, and this is a vapor jet, and then it blow up all the powder particles into air, and the ambient gas will flow in and entrain the surrounding powder particles inside. So the particle velocity actually agree relatively well with the experimental observation. So this is a results. So this is a vapor jet flowing in high speed. So the ambient gas will form a vortex and flow like this. So here surround the the particles nearby will be blow up, and the other particles neighboring particles will drag in. So this is denudation. So actually, with different set of laser power and scan speed, the vapor jet angle is different, like forward, vertically upward, and backward. So we also similar these different cases, and you can see for the backward case, there's almost no powder remain here. So you can see this is the case. And for the vertical vapor jet, there are the most powder remain here. So you can see here. And for in forward, it's like in the middle case. So qualitatively, they agree with the experiments. And with the melting simulation, we want to further investigate how the grain will evolve. So we impose the temperature field from the melting simulation, and also we implement a new collision model into the grain growth simulation. And we can see this is a grain growth. And the 3D view, and at the same time you can see this the pink spots are the nucleation size. So it's determined by the undercooling. Here the cross section may be even more clear. So you can see this is the first track, second track, and third track. You can see the columnar grain and the remelting of the previous track. And then the second layer will be rotated for 90 degrees. And this is the scan direction. This is the columnar grain. And we do some experiment to validate the model. And they also, the trend are pretty close. And also actually we have another model to simulate the dendrite growth. So first compare with the IGK model, and then we compare with the X-ray imaging results by some scientists in Japan. And we extract the value of the length of the dendrite trunk, and we can see in the simulation and experiments they are pretty close. Moreover, so particularly in electron beam polybed fusion, there will be the solidified material will be maintained at a high temperature. So there will be a serious solid state phase transformation and the precipitation process. And this is our simulation results for the precipitation process. And this is experiments. So still is we show some similar trends, and we can provide more useful guidance for the real experiments just through its simulation. And the ultimate goal for sure is we want to predict the mechanical property based on the fabrication parameter. So then we link this powder spreading, powder melting model, then with a grain growth model, so we can get the structure information including voids and grains. And then we implement into a crystal plasticity model to predict the mechanical property. So with this, we can replace most of the trial and error experimental procedures. For example, this is pod spreading, pod melting, SEM, EBSD characterization, and then tension compression test. So this is a collaboration with Shanghai Jiao Tong University. So they use additive manufacturing to fabricate copper. So they found there are high density dislocations, and then asked us to do some simulation about the temperature and thermal stress. And our simulation results show the tension compression cycles. So they believe Okay, because I'm not an expert in this area, so they believe, the origin of this high density dislocation in additively manufactured metals are due to the repeated compression and tension cycles of thermal stress. Okay, so I think your group are there are a lot of experts in this area. So if you are interested, I'm very happy to collaborate. Okay, so lastly, I want to briefly introduce our efforts in integrate data analytics with the multi-physics modeling, because the multi-physics modeling can review the physics, but also computationally expensive. So it's very limited in the engineering applications. So here I just want to show two cases. One is we built a powder scale simulation of the directed energy deposition, and we can simulate, the single track or multiple layer and also curved track, but it takes tens of or hundreds of CPU hours to finish this simulation. So instead of run a new simulation for new parameter sets, we use the available simulation results and then use a Gaussian process regression model to build a surrogate model. Then for the new model, for the new parameter set, we just use the Gaussian progress regression model to predict the track dimensions. And it's also agree pretty well with the experiments. So almost maintain the same accuracy with multi-physics simulation, but the computation speed is lower than the computation cost is lower than 1 second in a computer. And another is we want to use data analytics to analyze. There are so many factors in different assumptions in different models. For example, in our previous models, a lot of factors are incorporated, but in simplified models like Model 2 and Model 3, just the major physical factors are incorporated. So we run a lot of cases and then use data analytics to draw an error map. So this error map can provide guidance to the end users on how to select a model and what's their expectation of the accuracy, and also can provide guidance for the researcher in modeling, like which physical factors are significant and which modeling assumption is not reasonable, will introduce large inaccuracy. So due to time limitations, so I just very briefly introduce all of these models. So if you are interested, you can read our papers listed here. So I think that's all I want to share today. Thanks.
Thanks a lot. Yeah, why? Yeah. Right. So if you have some questions, please use the raise hand function, and I can arrange our Q&A sessions. Yes, Ben, please.
Thank you for the great talk. In terms of the earlier, so you showed later on some of the sort of physical comparisons between experiments and simulations. Earlier on, you showed beautiful sort of what we would call sort of mechanistic insight of looking at, for instance, the breakdown in the assumption of the sort of laser track, I think it was, in terms of for one example, and then you showed your simulation alongside. That would be a good example. Yeah, I guess one of the bits here is sort of in your sort of philosophy, how do you demonstrate that your model is sufficient to describe the problem? I can see the qualitative agreement is beautiful, but I guess, you know, what would confirm to me as someone who doesn't know that much about this particular problem why your model is quantitatively reasonable? How do you convince other people in that bit?
Oh, okay. Yeah, that's a very good question. So, like qualitatively, like the phenomenal, we, you know, experiments and simulation agree pretty well. And actually, we also have some, you know, so in the following, the quantitative validation is also good, including the direct comparison with the in situ X-ray imaging. Okay, so but the physical mechanisms or the explanations offered from our simulation, yeah, that's you know, but because in experiments we cannot say through any observation we cannot say this is the physics is like this, right? But from observation, all the phenomena, all the process, the forming process, the multiple depths, multiple lengths are all very well. So then we, you know, we believe the explanation from the simulation results are reasonable. So that means, you know, we cannot make sure every aspects of the simulation is directly validated by experiments. But as long as there are enough or quite a few significant values or phenomena are reproduced in the experiments, in the simulation, we think this simulation is reasonable, and conclusions from this simulation are reasonable, are convincing.
Thank you.
Okay, thanks.
Thanks. Yeah.
Sam, please. Yeah.
Yeah. First of all, thank you very much, Dr. Yang. That's fantastic work. It's very impressive. My question is similar to Ben's question. Follow up in particular focus on microstructure. So we did very nice work to link between the processing simulation and do the phase field as well to predict the microstructure. So my question is, have you verified your simulation? First of all, if you want to predict the microstructure, did you verify the grain growth with experimental observation? First of all, EBSD data, or do you verify? So I know you verified the dendrite spacing already, but have you done that in the either laser beam or electron beam melting to verify your prediction of, say, the dimension of the dendrites or dimension of cells, to see whether they be in a good agreement with the experimental observation?
Okay, that's a good question. So actually, when we do a simulation, we develop a model. Okay, so we first start from a simple case, like a casting case, you know, very well controlled case, like this X-ray imaging case for dendrite growth. So we validate against this kind of experiments, and then we go through more complex cases in additive manufacturing. But currently, the X-ray imaging of the current or dendrite growth in additive manufacturing, I haven't seen yet. So we don't have compare directly with in situ imaging. So mostly we just do post-processing experimental observation, like using EBSD and optical microscope or SEM to see the grain morphology and grain size, and then we usually, you know, compare the grain morphology and grain size. So in terms of this, but for direct validation, like where X-ray imaging, we don't have any experimental results, or we don't see any experimental results.
Yeah, thank you. That's very nice. Yeah, I do agree. That's very good. I mean, agreement there. So my a little bit kind of minor follow up is: have you say instead of only compare a specific region, or you can pick some region from university data to compare one layer or two layer of deposition. Have you done more multi-layer deposition simulation, and you have a data from simulation for the crystal orientation, and compare that with the university data for a little bit larger area, for example?
Oh, okay. So currently, for large area comparison, this not mainly constrained by our computation power. So you see, this this melting simulation actually it takes around 200 or 300 hours to run this simulation. And this one, we use multiple GPU to run this case, but it's still time consuming. So if we want to do larger simulation domain, we have to move on to a supercomputer.
Yeah, that's right. Yeah, that's a limit of the computational performance.
So now there's any people, even the U.S. national labs like Lawrence Livermore National Labs, they also have limitation for computational power. Although they maybe have the best supercomputer in the world, but still computer power is not unlimited. So I have to consider this constraint.
Yeah, thank you.
Okay, thank you.
Thanks, Song. Jingwei, I think you raise your hand.
Yes. So it's very great works and great models, Dr. Yan, and thank you very much. So I have just a continuous question extending, like maybe just a comment about the simulation about dendrite growth using the I think it's synchrone, right, by Professor Yasuda. I think in the synchrone experiment, this is just a comment. The cooling rate or the thermal gradient across that field of view is very small. But in the real, I think additive manufacturing, the cooling rate is much faster. So, and I don't know, like I think for synchrone X-ray imaging to work on the experiment on the real additive manufacturing might be very challenging at the moment. So I think it's better. It would be best if you can model the faster cooled dendrite growth, like more related with the additive manufacturing.
Yeah. So actually, I talked to the scientists in Argonne National Lab. So actually, I think you guys are pretty familiar with this X-ray imaging because I think Dr. Peter Lee did a lot of work with the diamond, right?
Yeah. Yes.
So
and also
my major collaborator is the Argonne National Lab. So I talked to them. So yeah, they tried to see the growing growth or dendrite growth in their X-ray imaging results, but it's too challenging. It's too fast.
Yeah, I can understand that. And also like we collaborate. We have Dr. Goli. We have collaboration with Professor Yasuda, the author of your site as well.
Oh.
Yeah. And so another comment is your model about nucleation so I think it's the next slide or the previous slide. So here in your model, like how I think the main factor in the equation might be the F theta, which is the geometric factor about the heterogeneous nucleation. And that's to my understanding. So how do you define, like how do you determine where are the nucleation sites? Because I believe the particles might flow and it's not quite fixed. So the geometry might change during the scanning. So in that case, how do you model where they nucleate?
Okay, so this is the work by my postdoc, Dr. Yang Ming. So based on my understanding, so which actually we assume the nuclear site is a static, don't move. So so now because we just consider like the the influence of temperature and the geometry. So
yeah, but
and actually we are not also adding the influence of chemical compositions.
Okay, yeah, but I think because it's quite flow, it's like, I don't know, like upon heating it will melt, so the geometry would change. So maybe it's better to consider that as well.
Right. So this is a very fundamental but also very significant problem.
Yeah.
And also actually we're thinking a lot in the fluid flow in the Martian zone. Yeah, because there are some experimental observation of the fragment of dendrite. So so this will make this kind of simulation even more complex.
Yeah. Great, thanks.
Any more questions? Right. No. So I think that's the time, and we schedule that until 11. So great. So it's our great honor, and it's a very pleasant presentation delivered by Dr. Yan. And if we have more, so because Jingwei has recorded the videos, and if we have some questions, we can discuss with Dr. Yan later on. And thanks a lot. And Dr. Yan, we will send the private link for the videos. And if you are happy, we will publish that on YouTube. And thanks for our group. Thanks a lot for joining us for the year seminar. This is the first one for our virtual sort of trial engineering alloy seminar, and we are quite keen to know your feedback and comments on the first virtual one. So therefore, we can improve in the later sessions. And so yeah, any comments and feedback is highly welcome. And thanks a lot for joining us today. Oh, someone raised a hand. Oh, it's Jingwei. Okay. Sang, you have any comments or something?
Yeah. So thanks for the invitation. So I'm very happy if you want to have anything to collaborate in terms of experiments and simulation. So actually, I read a lot of paper from your group. So especially by Dr. Min Song. Min Song.
Yeah, thank you very much, Dr. Yan, for, it's just very impressive work. I also read a lot of your paper as well, so I was impressed about the quality of work and the detail and the fantastic simulations as well. So yeah, thank you very much for accepting the invitation and give the wonderful presentation to us today. But also I want to thank Elon and Jingwei for very outstanding organizing the seminar, the first seminar remotely, and hopefully everyone enjoys the seminar today.
Yeah, no worries. And I think that's it. And thanks a lot. And if you are happy, and we're gonna just organize the following stuff. Right, thanks a lot, Dr. Yan, and thanks for your
thank you
again for everything. I know it's not very straightforward for us to deliver this talk directly. Okay, thanks a lot. Yeah. See you.
Bye.
Bye. Thank you.
Bye. Take care.